In this video, we shall be discussing how to draw shear force and bending moment diagrams of a simply supported beam, or in short SS beam. Hello friends, you are watching channel Number Collage. This channel features easy to understand concept videos on strength of materials. The first case that we shall consider is simply supported beam loaded at the midspan. Before we move further, let us first understand what is meant by a simply supported beam or SS beam. Consider a beam AB supported at its ends A and B. Let its span be L, is known as simply supported beam or SS beam. When it is loaded at the midspan W at point C, then distance AC will be L upon 2 and distance CB will also be L upon 2. The reactions at the supports A and B due to vertically downward loads RA and RB pass through the endpoints A and B. Before we move further to find the shear force and bending moments of this simply supported beam, we must first understand two important rules. The first is sum of vertical forces on the beam equals 0, and number 2, sum of moments about a particular point equals 0. Now according to the first rule, we have W, RA and RB, three coplanar forces, and their sum will be 0. So we write W, which is acting vertically downwards, so therefore it is plus, minus RA, which is acting vertically upwards, so minus RB, which is acting vertically upwards, so minus, is equal to 0. So that gives us RA plus RB equals W. So let us name this equation as 1. Here the reactions RA and RB are unknown, which we have to find out. For that, we have to take moments about either point A or point B. Let us take moments about point A. So, moment of load W about point A will be a clockwise moment because this load has tendency to rotate the beam in the clockwise direction about point A. So we write W multiplied by its distance from point A, which is L upon 2. Next, moment of reaction RA, which is passing through the point A about which we are taking the moments, will be 0 because its distance from point A is 0. Moment of reaction RB about point A will be anticlockwise because RB has tendency to rotate this beam in anticlockwise direction about point A. So we write this as minus RB multiplied by its distance from point A, which is L. Now this sum, according to the second rule, sum of moments equals 0, will be 0. So next we can write this will be WL by 2 equals RB into L. This L cancels with this L, so that gives us reaction RB equals W upon 2. We will substitute this value of RB here and write RA plus W upon 2 equals W. That gives us RA equals W minus W upon 2, that will be 2W minus W upon 2, or W upon 2. So we got both the reactions RA equals W upon 2 and RB equals W upon 2. So for the mid span point load, the reactions are symmetrical, which in this case are W upon 2 and W upon 2 each. So this is how we can find the reactions at the ends of a simply supported beam or SS beam. A simply supported beam AB of span 8 meter is loaded at the midspan with 100 kilonewton load, so that distance AC will be 4 meter and distance CB will also be 4 meter. Due to vertically downward load, there will be reactions RA at support A and RB at support B. We have to find out the values of RA and RB. We have sum of vertical forces FV equals 0. So 100, which is vertically downwards, minus RA vertically upwards minus RB vertically upwards equals 0. We have written vertically downward force as plus and vertically upward forces as minus. So that gives us RA plus RB equals 100. We name this equation 1. Now we will take moments of the various forces about point A. Next we have sum of moments about point A is 0. So moment of 100 kilonewton force will be 100 multiplied by its distance from point A, which is 4 meter. Now this moment tends to rotate the beam in clockwise direction about point A, so this is plus. Reaction RA passes through point A, therefore its distance from point A will be 0, so its moment will also be 0. So there is no need to write the moment of reaction RA. The moment of reaction RB will be RB multiplied by its distance from point A, which is 8 meter. Now this moment tends to rotate the beam in the anticlockwise direction about point A. So we write it minus, now which is equal to 0. So that gives us 8 RB equals 400, or RB equals 400 upon 8, which will be 50 kilonewton. 8 ones are 8 fives are 8 zeros are. Now using RB in this equation, we get RA plus 50 equals 100. So that will give us RA equals 100 minus 50, that is 50 kilonewton. So we got both the values of RA and RB. Now we will do shear force calculations. Shear force at point B, FB, will be minus RB because there is downward force to the left of point B, which will be minus 50 kilonewton. There is no loading between point C and point B, so the value of shear force to the right of point C will be same as minus RB, which is minus 50 kilonewton. Now shear force just left of point C, which is FCL, will be 100 kilonewton downwards minus RA, which will be 100 minus 50 upwards. So that will be plus 50 kilonewton shear force to the left of point C. Bending moments at the end supports will be 0. So MA equals MB equals 0, because there is no question of any bending at the supports. Bending moment at point C, MC, will be RA multiplied by distance of RA from point C, which is 4. This has tendency to rotate the beam in the clockwise direction, so it will be plus. Value of RA is 50 multiplied by 4, so it will be plus 200 kilonewton meter. For shear force diagram, let us first draw baseline AB. FB is minus 50 kilonewton, which we plot somewhere here, and FA is therefore 50 kilonewton, which we plot somewhere here. So this is minus 50 RB, this is plus 50 RA. The shear force curve will be a straight line from A to C, as there is no loading between A and C. The shear force curve will be horizontal from B to C, as there is no load between C to B. So this will be shear force diagram, which is positive here and negative here. For bending moment diagram, let us first draw the baseline AB and C. Bending moment at point C, MC, is 200. Say it is here. Bending moment at point A is 0 and that at B is 0. So we will complete the bending moment diagram by joining 0, 200 and 200 to 0 at B. So this will be the bending moment diagram, which is totally plus, and it is sagging type because it has tendency to sag this beam like this. Hence it is drawn above this baseline AB, SFD, and this is BMD. In the next question, there is a simply supported beam AB of span 9.75 meters carries an UDL of 10 kilonewton per meter. We have to find the magnitude and position of the bending moment developed in the beam. Let support reaction at A be RA and support reaction at BRB due to the UDL 10 kilonewton per meter. According to sum of vertical forces equals 0, we write RA plus RB equals the UDL 10 multiplied by its span 9.75. So that will be 97 point T kilonewton. Name this 1. Next, we have summation of moments about point A equals 0. So taking moments about point A, we write UDL 10 multiplied by its span 9.75. Now this load will act at the midspan, that is at 9.75 on 2. This moment tends to sag the beam like this, so it is plus bending moment minus RB multiplied by its distance from point A, which is 9.75, which is equal to 0. So that gives us 9.75 RB equals this calculation, which is 475.312. So RB will be 475.312 upon 9.75, which will be 48.75 kilonewton. So this is RB, which we write here 48.75 kilonewton. Using this value of RB in equation 1, we write RA plus 48.75 equals 97.50. So the RA will be 48.75. Here we observe that the loading is symmetrical. Both RA and RB are the same, and each one of them is half of 97.50. So for asymmetrical loading, we can directly write the values of RA and RB without doing all these calculations. Now we have RA equals 48.75 kilonewton and RB equals also 48.75 kilonewton. Now in shear force calculations, we have shear force to the left of point A equals 0 as there is no load. Shear force to the right of point A 48.75 kilonewton according to downward load to the right of point A. Shear force to the left of point B will be 48.75 upwards minus UDL 10 multiplied by its span 9.75. So that will be according to upward load to the left of point B, which will be minus 48.75 kilonewton, and shear force to the right of point B will obviously be 0 as there is no load. There will be maximum bending moment at point C, so shear force at the midspan C is 0. For drawing shear force diagram, let us first draw baseline. Then shear force to the right of point A is somewhere here, which is 48.75 kilonewton, and shear force to the left of point B minus 48.75 kilonewton. We will complete the shear force diagram by joining plus 48.75 and minus 48.75. So this is the shear force diagram, which is positive here and negative here. So this is SFD, shear force diagram. We have to find the position of zero shear force or point of contra shear. So let the position of the point of contra shear PCS from the end A be x meter. Sum of shear force at point C is 0. So we write RA minus 10 multiplied by x equals 0, but RA is 48.75, so 48.75 equals 10x. So that gives us x equals 48.75 upon 10, so that will be 4.875. So the position of point of contra shear from point A is 4.875 meters. Now for bending moment calculations, we know that the bending moment at point A, MA, equals bending moment at point B, MB, equals 0, as there is no bending at the end supports. Now bending moment at point C, MC, will be RA, which is 48.75 kilonewton, multiplied by distance x, which is 4.875, minus UDL 10 multiplied by 4.875, which is x, multiplied by half of x, that is 4.875 upon 2. So this calculation gives us bending moment at point C, MC, equals 118.828 kilonewton meter. Now for drawing the bending moment diagram, we will first draw the baseline. This is A, this is B, this is C. The maximum bending moment occurs at point C. Let this be MC. And since this is an ellipse and it contains product of two distances, it's going to be a parabolic curve. So we draw the bending moment diagram from zero bending moment at A, parabolic to maximum bending moment MC at point C, then from MC to zero bending moment at point B. So this is the BMD of this loading, which is positive. At the point of maximum bending moment, the shear force is 0. A simply supported beam with point load at any position on it. Consider a simply supported beam AB of span 5 meter loaded as shown 30 kilonewton at a distance 1 meter from point B and 15 kilonewton at a distance of 1 meter from point A. Let these points be, this is C, this is D. Naturally distance CD will be 3 meter. We have to draw the shear force diagram and bending moment diagram. Support reactions due to the load at point A is RA upwards and RB upwards. The loads RA, RB 15 kilonewton and 30 kilonewton are coplanar and non-concurrent forces, and we have sum of vertical forces equals 0. So therefore vertically upward forces RA plus RB equals vertically downward forces 15 kilonewton plus 30 kilonewton. So that will be RA plus RB equals 45 kilonewton. Name this equation 1. Moments due to the various forces about a particular point is also equal to 0. So we write summation of moments about A, because we are going to take moments of the forces about point A, which is equal to 0. Now moment of load 15 kilonewton will be 15 multiplied by its distance from point A, 1 meter. This will be plus because it's going to rotate the beam in the clockwise direction about point A. Moment of load 30 kilonewton about point A is plus 30 multiplied by its distance from point A, which is 3 plus 1, that is 4 meter. This is also going to be plus because it's going to give clockwise moment about point A. Then moment of reaction RB will be RB multiplied by its distance from point A, which is 5 meter. Now this moment is going to rotate the beam in the anti-clockwise direction like this. So it will be minus, and moment of reaction Ra will be 0 as it is passing through the point A about which we are taking the moment. So all this is equal to 0. Now that will be 5 Rb equals 15 plus this 120, so that will be 135, and that gives us Rb equals this 135 upon 5, which will be 27 kilonewton. We will use this value of Rb here and find Ra, which will be 45 minus 27, which will be 18 kilonewton. So we have Rb equals 27 kilonewton and Ra equals 18 kilonewton. Now we will find shear forces. Shear force just left of point B, that is FBL, which will be minus 27 because there will be downward force to the left of point B. So this will be minus 27 kilonewton. As there is no load between points P and D, shear force to the right of point B will also be same as to the left of point B. Therefore, FBR will be also minus 27 kilonewton. Now shear force just left of point D will be equal to minus 27, which is Rb in upward direction, plus 30 kilonewton point load acting downwards. So that gives us FDL equals 3 kilonewton. So this is 3 kilonewton. Now shear force to the right of point C will be same as shear force to the left of point D, as there is no load between points C and D. So FCR will also be equal to 3 kilonewton. Next, shear force to the left of point C will be equal to this 3 kilonewton plus 15 kilonewton point load acting downwards. So that will be FCL equals 18 kilonewton to the left of point C. And finally, shear force at point A, FA, will be same as the reaction RA, which is 18 kilonewton. Or since there is no loading between points A and C, the value of Fa will be same as value of FCL, that is 18 kilonewton. So let us draw the shear force diagram from these shear force values. So first let us draw the baseline A, B, C and D. First shear force Fa 18 kilonewton, then shear force FCL 18 kilometers again. As there is no load between A and C, the shear force curve will be horizontal. Then shear force to the right of point C is 3 kilonewton and to the left of point D is also 3 kilonewton. So the shear force curve will be horizontal from 3 to 3. Then shear force at point B is 27, let it be here, and shear force to the right of point D will also be minus 27. So the shear force curve will be horizontal from minus 27 to minus 27. So this will be the shear force diagram, partly positive here from A to D and negative from point D to B. So this is shear force diagram and this is the baseline. Now next we will calculate the bending moments. Bending moments at the end supports will be 0. So therefore MA equals MB equals 0. Bending moment at point C will be MC equals RA multiplied by its distance from point C, which is 1 meter. So it will be 18 multiplied by 1. So that will be 18 kilonewton meter. Now there is clockwise moment to the left of point C. So this will be plus 18 kilonewton meter. Next, bending moment at point D will be equal to Rb multiplied by its distance from point D, which is 1. So this will be 27 multiplied by 1. which will be 27 kilonewton meter. This will give a clockwise moment to the right of point D, so this will also be plus. Now we will draw the bending moment diagram. For that, first let us draw the baseline A, B, C and D. Next we will plot MC, which is, say here, 18 kilonewton meter. Then MD, which is 27, say here 27 kilonewton meter. Bending moment at point A is 0 and that at point B is also 0. So the bending moment curve will be from 0 bending moment at A to 18, then from 18 to 27 at point D, and from 27 to 0 at point B. So this will be the BMD, which is positive, hence drawn above the baseline. Next, simply supported beam is of span 6 meter. Let's name it A and B. There is UDL of 3 kilonewton per meter over AD, whose span is 2 meter from point A. There is a point load of 6 kilonewton at point C, which is at a distance of 2 meter from point D, and the remaining distance CB will be 2 meter. Let us find the reactions at the simply supports A and B. Reaction at point A is RA and that at point B is RB. So according to first rule, sum of vertical forces equals 0 gives us vertically upward forces, that is reactions RA plus RB will be equal to downward UDL 3 multiplied by its span 2 plus downward point load 6, so it will be 12 kilonewton. Next rule is sum of moments about any point, say about point A, equals 0, so that gives us UDL 3 multiplied by its span 2 multiplied by its midpoint, which is 2 upon 2, that is 1, and this will be clockwise moment about point A, and moment of point load 6 kilonewton about point A will be 6 multiplied by 2 plus 2, that is 4. Moment due to reaction RB about point A will be anti-clockwise, so it will be negative, so we write minus RB multiplied by moment arm, which is 6 meter, so this is equal to 0. Now that gives us this 6 RB equals 6 plus 24, that is 30, which will be reaction RB equals 6 5s are, that is 5 kilonewton. Using this relationship we get RA equals 12 minus 5, that will be 7 kilonewton. So RB is 5 kilonewton, RA is 7 kilonewton. Now let us write shear force calculations starting from point B. For shear force diagram, we will draw the baseline first, A, B, C, D. Now we will write SF calculations. So shear force at point B will be equal to minus reaction RB, because there is no load at point B to the right of point B, and downward force to the left of point B. So therefore FB will be minus RB, that is minus 5 kilonewton. We will plot at this point 5 kilonewton, which is below the baseline AB. Next, shear force to the right of point C will be same as minus RB, as there is no load between points C and B, so it will also be minus 5 kilonewton, which we plot over here. So this is also 5 kilonewton. We will draw a horizontal line, and this completes our shear force diagram between points B and C, which is going to be negative. Next we write shear force to the left of point C, which will be downwards point load 6 kilonewton plus FCR, which will be 6 minus 5, and that is 1 kilonewton. Now this being plus, we will mark it over here, so this is 1 kilonewton. Next we write shear force at point D. As there is no load between points C and D, FD will be same as FCL, that will be 1 kilonewton. So we mark it over here, draw a horizontal line, and this completes shear force diagram between points D and C. Next we write shear force at point A, FA, that will be point load 3 multiplied by 2, 6 plus FD, which is 1. So it will be 6 plus 1, 7 kilonewton. So this shear force we mark over here and join points 7 and 1, and this completes shear force diagram between points A and D. This will be positive and this also will be positive. Next we will write bending moment calculations, and for that we will first draw the baseline AB. Now first bending moment about point A will be 0 because it is endpoint simply supported. Bending moment at point C will be MC, which will be according to the sign convention this RB, which is 5 multiplied by its moment arm, which is 2. So it will be 10 kilonewton meter. So we will mark it here MC, which is 10 kilonewton meter. Next, bending moment at point D, MD will be according to the same sign convention. Bending moment due to reaction RB, which is 5 multiplied by its distance from point D, which is 4, then minus 6 kilonewton, which is this, multiplied by its distance from point D, which is 2. So it will be 20 minus 12, that is 8 kilonewton meter, which we plot over here, and MB will also be 0 because that's the end point. From A to 8 it will be quadratic bending moment curve. From 8 to 10 it will be linear curve. Then from 10 to B it will be a linear curve again. So this is the bending moment diagram BMD, which is plus, so above the baseline. Friends, if you like this video, please click the like button. Share this video with your classmates. Don't forget to subscribe this channel to get more videos of this type. Give your comments to make these videos better. You can suggest topics on which you want me to make videos. See you in the next video. Until then, keep watching Number Collage. Thank you.